Okay, so our bell work today is basically related directly to what we did yesterday. It's not asking you to go through and find the confidence interval, but it is asking you to figure out the calculation required for that. And what you hopefully remember is that that's going to be p hat plus or minus your critical value z star times the square root of p hat times 1 minus p hat all over n. N, of course, is your sample size, 1,250. So I know that this is going to be, if I kind of start plugging this in, this is going to be 1,250 at the bottom. Now, every single answer choice has that. That doesn't do us much good. My Z star, it's a 95% confidence level. So I know it's going to be 1.96. Again, all 5 choices have that as the critical value. So that doesn't help us out much. But here's one thing we can notice. The entire fraction on the right should be under the radical. And when I look at my answer choices, 3 of them are not set up that way. So automatically I've narrowed it down to B and D. So the only difference between these two is what goes in the numerator of this fraction. And remember, that's p hat times 1 minus p hat. Your p hat here is the 450 out of 1,250. That calculation gives you 0.36. So the correct answer is D. It's important to realize that this 10% right here that they're talking about is part of the prompt, is part of the question that was asked of these people. Would you cut your driving by 10%? That could have been any percent. Would you cut your driving by 5%? And regardless, it is not the p hat that we are looking for this problem. So hopefully if you made a mistake on that, you caught where you made your mistake and you're feeling good about it now. All right. Okay, you can see lots of headings for today, but really we get down to the big one here, the one sample t interval for mu. Woohoo. And luckily this builds a whole lot on what we did yesterday. We're just going to run through a few of the differences between the proportion we did, the interval for proportions we did yesterday and the interval for means that we're doing today. We're going to start off with the other practice problem from yesterday. And hopefully you guys did this. If you did, you can just compare your work against what I'm about to do here. If you didn't, we're going to run through it. It's really, really important that you guys are getting comfortable with the full process of constructing confidence intervals because, well, it's something you need to know. And just kind of related to that, those of you who are planning on doing the AP test, now is the time where you need to start contacting and getting that paid for. You have to register now if you want to take it in the spring. You can't decide later. So I highly encourage you guys to do that. You will have review sessions between now and then. You'll be able to remember the stuff. You guys are going to do great. I encourage you to give it a shot. And we learned a little bit about expected value. This is a brief tangent. Your expected value here, if you give yourself a 20% chance of passing that test, getting a 3 or higher, so you got an outcome of a probability of passing of 0.2, which means 0.8 that you don't get that. That doesn't sound that great. We can do some expected value real quick. It says, well, let's say that you save yourself $4,000 by taking this class, getting that college credit. It might not be that much. Let's say 3,000. So on the chance that you pass it, you save yourself $3,000. That's $3,000 in your pocket or your parents' pocket or whatever. But if you take this test and you fail it and you don't get the credit, you're out $94. So we can find our expected value. We can do that real quick. Let's see, 3,000 times 0.2 plus 94, negative 94 times 0.8. Oh man, this is looking pretty promising. That's an expected value of $524.80. Look at that. You're throwing away $500 by not taking that AP test. And we got to review some statistics while we did it. How fun is this? This Friday's off to a great start. Okay, we are now going to construct a confidence interval for the true proportion of Arizonans who won't vote in the election. according to this made up poll right here. So remember, what we first want to do is state the parameter, and we want to estimate the confidence level. So our parameter here is, we're trying to find P, the population proportion, which is the true proportion of non-voters in Arizona. Of course, we're talking about non-voters who could have voted specifically. The confidence level, well, that's easy enough, that's 95%. And this is a very common one. So before long, hopefully you guys memorize your critical value for this. You might already know it, 1.96. It's always available in that table B. All right, 1.96, we're ready to move forward. Identify the appropriate inference method. Well, I look at this and I can see I'm dealing with proportions. It says proportion right here. I know it's proportions. I've only got the one sample right here. So that to me looks like a one sample. And it's going to be a Z interval for P, proportions, population proportions. Okay, our conditions. We need to check three things. Was it random? Well, I'm looking at this, randomly selected. Oh, yeah, it's random. Does it meet the 10% condition? Well, is 1,423, that's our N right here, is that less than 10% of all the Arizona voters? I believe it is. So that's less than 10% of the population, which means we can use a simpler calculation, which is the calculations we're going to use. And the last one, is it normal? So for us, that means doesn't meet the large counts. And n times p and n times 1 minus p both have to be greater than or equal to 10. Now, with this big of a sample size, yes, it is big enough, okay? But it is worth it right now to figure out what our p hat is. Now, I guess for this, we're technically doing p hat. But our p hat in this case is going to be 415 divided by 1,423. And that is 0.2916. Okay. So, I mean, yes, I could go through and do the multiplication here. I'm being a little bit lazy right now. It's going to be over 10. I think you guys can all see that. So we're good with large counts. This is normal. So now we can use normal CDF. Okay. And we're not using normal CDF for this calculation, but for others we would. All right, so now we're going to do the calculations. And the first thing we want to remember is the general formula for any confidence interval. This is on your formula sheet. It's the stat plus or minus the confidence, or sorry, not confident, the critical value times the standard error. And it's really beneficial as you're going through a problem like this to include all of these steps where you start at the general and work your way toward the specific. So now we're going to get a little more specific. Our stat is going to be p hat plus or minus. The critical value is going to be z star because it's a z interval. And the standard error is going to be the square root of p hat times 1 minus p hat all over n. Just to keep repeating myself, you don't have to have this memorized. If you can find the standard error for your interval, you can just plug that in for this. If you know what the stat's supposed to be, you can plug that in, and so on. So now that we've got this, I'm going to actually just plug in the values, and we will come up with the confidence interval. So it is going to be 0.2916 plus or minus Z star is 1.96 times the square root of 0.2916. And 1 minus that should be 0.7084 divided by n, which is 1,423. I will leave that right there. You guys can calculate the confidence interval. Okay, so we've got our interval and the last step. This is incomplete until we provide an interpretation. And our interpretation follows a template. And the sooner you can kind of learn this and be able to fill this template in with the new context, then the easier it's going to be for you. We are, let's see, 95% confident that the interval from, now we just plug in these numbers, and remember you could write it as decimals. I'll write it as percents here. 26.8% from 26.8% to 31.52% captures the true proportion of non-voters in Arizona. And one thing I would say, and this is probably not anything that's going to come back to bite me, but just to make sure it's absolutely flawless here, maybe it would have been better if I'd used the exact phrasing. The proportion of Arizonans who said they don't plan to vote in the upcoming election. If I'd used that exact phrasing from the question stem, that might have been a little better. I don't think I'm really getting myself into trouble with what I did, but you know, it's easy enough just to straight up copy from the question. Okay, the only other thing here that I should have maybe done a little more on was explain this a little better. I did that the lazy way. Now I did show that I checked my conditions, that's good, but I didn't really provide a whole lot of details there. You don't need to write a paragraph about it, but you can just kind of do something like this, randomly selected. Yeah, it's random. You know, just whatever you can do to show, write a little sentence about your normal, or sorry, your 10% condition, something like that. So besides that, that's a pretty complete answer, I would say. All right. So let's look at this. We just wrote that down. Hopefully you still have it. Your friend thinks that this election is historic and that record numbers will come out to vote. He claims that 3/4 of all eligible voters will vote. Is his claim plausible? And what I meant, I hope you wrote, here's the confidence interval. So is his claim that 3/4 of all eligible voters will vote, is that plausible?
No. Wait, yes.
And this, when this question is asked, because fifth period had kind of the same sort of confusion with this question. And so that's why it's worth talking about here for a minute. We are answering this statistically. Now, statistically, if 3/4 of all eligible voters vote, then 25% didn't vote. Now, what we're saying is that at a minimum with 95% confidence, at a minimum, 26.8% are not going to vote, which means that at most 73.2% will vote. Now, this is statistically an incorrect statement that 3/4 are going to vote. Well, we can say right now, no, that's not going to happen. Okay. Now, that's a statistical answer. And then there's like real world. Are we really going to get, make a distinction between 73.2% and 75%? No. And if it happened to be 73.2%, we'd say, man, you nailed that. You said 3/4 were going to vote. You got it right. Yeah. In reality, we don't make a distinction between this. But statistically, it's not really looking possible that 75% are going to go out and vote. So I just want to make sure that's clear. And so the real takeaway is that if the value that's being claimed is within the confidence interval, then it's plausible. If it's outside the confidence interval, it's not plausible. So I know we're splitting hairs, but it's important to be able to, it's really kind of interpreting the confidence interval when we do that. Okay, now we're going to be looking at this scenario for quite a while. I decided to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. I am very, very serious about Oreo cookies, okay? I selected a random sample of 30 cookies and found the weight of each cookie in grams. I cannot emphasize this enough, how important this is to me. The mean weight, X bar, was 11.1921 grams with a standard deviation of 0.0817 grams. I went and bought a specific scale that can measure down to 10,000ths of grams for this particular problem. Now we're going to make a 95% confidence interval to estimate the true mean weight of Oreos. So we've got some data to work with. We're going to create a confidence interval. But first of all, what is our point estimate?
X bar.
X bar. So I'll just put X bar and I'll just write what that is. 11.1921 grams. All right. So we're going to go through this. This is kind of preliminary stuff before we get into calculations, because it's important to kind of put this into proper context at the beginning. We're going to identify the following. What is the population of interest in this problem?
The 30 cookies.
That is something, but it's not our population. We will bring up the 30 cookies.
Is it all Oreos?
That's it. All Oreos. So like when we're doing those polls on voting or not voting, voting for Trump versus voting for Biden, we're really interested in the population, which is all of the voters in a state or across the country. But all Oreos is the population here. And the parameter that we are estimating
Is that going to be the 30 Oreos?
No, that'll come up and we'll use that one in just a minute.
Is it the weight?
It's the weight. Yeah, and specifically, it's mu, which is the true, if I can spell, that says true, mean weight for Oreos. And that says Oreos, trust me. So it's the population mean weight. Okay, now the sample. What is our sample?
The 30 cookies.
There it is. It's the 30 cookies. And the statistic is Just as a hint here, the statistic is what we're using to estimate parameter.
11.1921.
There it is. This is just a repeat of what we already wrote down. It's X bar, which is 11.1921. And specifically, this is the sample mean. So remember, what we're getting into with inference is we're moving away from this perfect knowledge of what the population is. And we are now only working with samples and then making inferences about the population from that, which is really the heart of statistics. So we're getting into real statistics now. Everything else is just all the different lead up to this kind of stuff. All right. So good to be aware of that. And let's now look at this. We're going to check our assumptions. There it is. First of all, is it random? Someone identify how we know if it was a random or not.
It says random sample in the question.
There it is. Perfect. Thanks, Maggie. So random sample right there. Yes, it's random. Now this is where I'd want to say, maybe a sentence. The sample was random. Maybe I could underline that in the problem. It's just very, very clear. Yes, I checked this. And because it's random, now we know we're working with an unbiased estimator. This is maybe the most basic condition, but it's also the most fundamental one. We can do workarounds if it doesn't meet the 10% condition. We can do workarounds if it doesn't meet the large counts condition. But if it's not random, there's nothing we can do to fix the problem, okay? So it has to be random in order for this analysis to be worth anything. All right. Now, when I say we can do workarounds for those other things, that's if you continue in statistics at the collegiate level, not in this class. Okay, I decided to estimate the average. Oh, I already read that. Sorry. The next assumption is 10%. All right. Did we meet the 10% condition? And big N right here refers to the population size. Is our sample size less than 1/10 the population?
Yes.
Very clearly. 30 cookies is a tiny, tiny fraction of that. So we could say something to the effect that 30 cookies is less than 10% of the population of all Oreo cookies. You put 3 O's in that. Cookies. Okay, 2 I's. Man, I'm just on a roll. Looks like Wookiees. Okay, because it meets the 10% condition, we can use simpler formulas. We don't have to worry about more advanced statistical techniques. We can use the simple stuff. Okay, now the last assumption is normal. And this is where we need to run through this because we haven't really talked about checking normality. I threw out just really quickly, and we'll do it again, that when we're dealing with means, I mentioned this before, if we look at the sample size, if our sample size is greater than or equal to 30, oops, how did I put, I was thinking of N times P. I was just writing reflexively. So if it's greater than or equal to 30 as a sample size, then it is approximately normal because of the central limit theorem. All right, so the central limit theorem, as a reminder, says no matter what your population distribution is, this is a skewed right distribution right here, your sampling distribution will be approximately normal if you have a big enough sample size. If it's not big enough, the sampling distribution will still be skewed to the right. But if it's big enough, you will get a normal distribution. And how do we know if it's big enough? Well, that's if N is greater than or equal to 30. That's the number that statisticians have come up with. And so that's what we use. Okay. So if it's normal, we can use normal calculations, which makes our lives a lot easier. So to spend a little bit more time with that, checking normality for means specifically, because with proportions, it's pretty easy. You have your large counts condition and that's it. N times P and N times 1 minus P both have to be greater than or equal to 10. But with means, we have kind of a few things we can check. The most basic is this. If the population is approximately normal, then your sample will be approximately normal, okay? And there can be question prompts that say the sample size of 10 was drawn from an approximately normal population of ... And so you're like, oh, it's approximately normal, so sample size doesn't matter at this point. All right, the sample size is at least 30. And at that point, the central limit theorem is what kind of takes over, and we end up with an approximately normal sampling distribution. So that is going to be sufficient for us to call it approximately normal. This last one is a last resort. In fact, it says it's a last resort. If the sample is less than 30 and we're not sure about the population, really I should cross this out. So if it's less than 30 and we're not sure about the population, we can still assume normality for the sample if the sample distribution is approximately normal with no outliers or skew. So I can actually take my sample and create a distribution out of it. And if my sample looks like that, actually, let me go back. Let's say it was this one. Notice that sample size 10, and we end up with a distribution that looks like that. If that's the case, I can say, yeah, it's probably normal. We can assume that we're good to go. Okay. So that is a last resort, and generally speaking, I'm not sure you're ever going to need to use that condition. So really you're looking, is it an approximately normal population, or do we have at least 30 in the sample? And once we know it's approximately normal, like we said before, you can use normal calculations. So these conditions generally will be met by everything, but you still need to check them. Okay, and now let's start thinking about the calculations. Here's what we need to know. We need to know the statistic, the critical value, and the standard error. The statistic is already known. It's our point estimate, which we've already talked about. So now we need to know the critical value and the standard error. And we're going to start with the standard error, just like yesterday. That one's the easier one to talk about. And we need to remember a couple of things. Here are a couple of formulas for sampling distributions for means. So the mean of your sampling distribution of means is going to be equal to the population mean. And the standard deviation of a sampling distribution of means is going to equal this population standard deviation divided by the square root of n. Saying that makes it sound way more complicated than just seeing the formula. Okay, so there you go. Now with this one, we're dealing with one sample. We don't have the population mean at our disposal. So we're just going to be using X bar. Sorry, I don't know if you had a chance to see that. We're just using X bar. We're going to kind of throw this out. We're estimating this. Now, just like yesterday, because we don't know the population standard deviation, we're going to use the sample standard deviation for our estimate. And besides that, there's no real difference between these two formulas, but this on the right is our standard error, and that's standard deviation. Important to understand that this notation needs to be different for this. The standard error. Okay. And now, if we plug some values in, we can see our X bar is the statistic. This sample standard deviation divided by square root of n will give us a standard error. And we could even calculate the standard error right now. And you don't need to worry about it. I mean, you don't need to worry about writing it on the screen or anything. But you could take a second real quick and figure out what the standard error is going to be. So there we go. That should be, and you should think the decimal didn't show up, but yeah, 0.015 or 0.0149, however far you went with it. Very good. So just keep in mind the standard error is its own calculation. You can find that because you could very well come across a problem where it gives you all this information and the only thing it wants you to answer is what's the standard error? And you need to know how to find that. Okay, now the rest of it. What is the critical value for this? It would be great to say, oh, 95% is 1.96, but it's not that simple when it comes to means. All right, because we're not dealing with a normal distribution, which is weird. I know you're checking for normality, but there's something a little bit more to it. And it's not that complicated in the long run, but it's a little bit weird at first. We're working with what we call a t distribution. And well, maybe I'm jumping ahead here. So when we were working with proportions yesterday, the only parameter being estimated was the population proportion. So you had a sample and maybe whatever it happened to be, you got a p hat. Now I want to show you the formula real quick for our confidence interval, which you've seen before, but we need to look at it one more time to make something very clear. Is that ignoring the critical value, which is defined based on our confidence level, and n, which is a known value based on their sample size. These, if we ignore these two real quick, the only value we need to calculate the confidence interval is p hat. There's only one source of error, one source of uncertainty. All right. So you can be a lot more certain with your answers when you're working with proportions, because there's only one thing you're estimating. And we need to contrast that now with means, because we don't just have one parameter being estimated, we have two. We are estimating the population mean by using the sample mean. We are estimating the population standard deviation by using the sample standard deviation. Those are two sources of error. And with those two unknowns, that increases the uncertainty in our confidence interval. So we need to be maybe a little more cautious, make our intervals a little bit wider, because there's uncertainty, and this creates what's called a t distribution. And we're going to look at something real quick related to that. As our sample size gets bigger, our uncertainty gets less and less. Okay. So let's look at this real quick. All right. So what you have is this dashed line is a normal distribution. The orange is what's called a t distribution, and also called a student's t or student t distribution. Student comes from the fact that when this was kind of being formalized and written about, it was written by someone who just labeled themselves as student. You can look more into that story. It's not important for us. Okay, so right here, this slider, this DF means degrees of freedom. We're going to talk about that in a minute, but it can go down to 1 degree of freedom up to 30 degrees of freedom. Of course, you could have more than that, but notice that as this is lower and lower, it looks less and less like the normal. But as I increase it, and I'll do it slowly so that lag doesn't affect it too much. But as I keep going up with this, it looks more and more like our standard normal distribution. When we get up to 30, it's not much different at all. But in every single case, here's the main takeaway, and I'll go back down to the extreme end. In every single case, our tails are a little fatter. And practically speaking, what that means is that there is more possibility for something to end up out here in a t distribution than there is in a normal distribution. Like, look at the probability that something's going to be at 4 standard deviations or higher. It's practically 0 in a normal. But with the t distribution, something being 4 standard deviations away, well, it's not unlikely compared to the other. So the fatter tails means that there's more likelihood of your sample mean or something like that ending up way out here. And that's just an important distinction to be aware of. And no matter, even if I jumped up here to like 24 degrees of freedom, you'll still see that that orange is slightly higher than the dashed line. Okay, now as this goes up toward infinity, the degrees of freedom, it basically becomes the normal distribution, which is why yesterday when we were looking at our table B, the very last row showed infinity, and then you had your values. Because it's an infinite number of degrees of freedom, But just to summarize this one last time, we have more uncertainty because we have two unknowns that we are estimating for our calculation, which makes it less certain. Okay, so now we need to figure out how to find our critical value. And before we can do that, we need to talk about degrees of freedom. This is kind of a I don't want to say confusing. It's just kind of a weird topic at first, but it'll make sense after we look at a couple examples. Imagine you have a collection of 7 hats, and for the next 7 days, you want to wear a different hat. On day 1, how many options do you have?
Seven.
7. This is going to be really complicated, guys. On day 2, how many options?
6.
6.
Oh, okay. Let's see if you can get the next one. What about the 3rd day?
5.
5. I'm not going to make you do this for every single day. Okay, so for the next ones, you've got 4 options, and then 3. Now for day 6, you've already worn 5 of your hats. You only have 2 to pick from. And then it gets to the last day, and you have 1 option, right? So when it really comes down to it, I got to, I had 7 hats. I got to make a choice on day 1, 2, 3, 4, 5, and 6. But then on the 7th day, because I'm sticking with this wearing a different hat every day, I have to wear that 7th hat. So my degrees of freedom here is going to be 1 less than the number of choices. So my degrees of freedom, 7 minus 1, I had 6 degrees of freedom. Okay, because that last day, I didn't really have the choice of anything. Now, that's a little bit abstract, so we can put it in more of a mathematical sense. Imagine you have a sample mean of 10 and a sample size of 4. So in this sample, what could the first value possibly be?
Ten.
10. All right, that's fair. So the first one happens to be 10. The second one, what's the second one going to be?
10.
Are you going to do this seriously? And then the third one, what's that?
I'll say 15 this time.
Okay, there we go, 15. All right, so the last one, what does it have to be?
5.
5. All right, now for the first 3, you got to pick. For the last one, you did not. We already know we have a sample mean of 10 and a sample size of 4. So 3 of them, we have some latitude to kind of pick whatever numbers we want, but that last one had to be whatever the remainder was to get us up to 40. So of course we could change the numbers around. So if I did 12, 12, 12 for the first 3, then that means the last one has to be 4. All right, so in this sense, our degrees of freedom is going to be 4 minus 1 equals 3. We had 3 values we could decide for ourselves. Anyways, you get the idea. So the main takeaway from this is that your degrees of freedom will always be 1 less than the sample size. And we've already been seeing this notation, but degrees of freedom is frequently abbreviated as DF. Not much to it. And it's important to be able to look at a problem and identify the degrees of freedom. So how do we find the degrees of freedom? It's just going to be the sample size. Well, it just said that sample size minus 1. So in this our example from before, we had a sample size of 30. So we have 29 degrees of freedom. Okay, but now let's kind of see what to do here. We've got our T table, also called table B on the formula sheet. And what we're looking at is T star. That's our critical value. It's a T distribution. And it's really important that you identify the difference between T star and Z star when you're identifying this, because proportions use Z star, means use T star. I'm saying a lot of stuff that you guys are probably already grasping, so I apologize if I'm being unnecessarily specific and redundant. Okay, so now we've got table B. This might be big enough where we don't need to change, but it's a little bit hard to read this. I apologize for that. Hopefully you can still read it well enough. For my problem, I know that we had a, what's the word I'm looking for? A confidence level. That's the word I was looking for. Confidence level of, was it? Yeah, it was 95%. Was that right? Shoot, I forgot. I need to go back. I forgot what our confidence level was, unless one of you guys remembers. Um, 95%. There we are. So, forgot that for a second, but we can always go back and check. All right, so we had a 95% confidence level. That's what we're working with. So I'm looking at this column right here, and I found the 95% at the bottom of the column. And I've got 29 degrees of freedom. So here's my 29. And it's kind of hard to read that, but of course, you can pull that up on your iPad. That's 2.045. So it looks like my critical value found in this table is 2.045. And we're good to go. So we'll talk about what happens if your degrees of freedom is not on this. We're going to have an example of that in just a second, because this has every value up through 30, but then it skips up to 40, 50, 60, 80, 100. Of course, I want you to also notice the difference. Look at the difference between 100 degrees of freedom and 1000 degrees of freedom. It goes from, like right here, 1.984 to 1.962. Not much of a difference between those two. And then going from 1000 up to infinity, this only changes by 2 1,000ths. So as you keep adding degrees of freedom, the exact number becomes less and less important. Okay. So anyway, 2.045 for our particular problem. And we end up with a generic formula right here. We'll remember that 2.045. This is it. This is our one sample t interval for mu. X bar plus or minus our critical value t star times the standard error, which is the sample standard deviation over the square root of n. Okay. So we're just doing this math, or like I've already done this math for us for this. So we found the 2.045 on the table. That's our critical value. And the final confidence interval when we do this is going to be between 11.1616 and 11.2226. I'm very serious about Oreos. Let's just make sure that's clear. When we calculate this, the final confidence interval is that. So the question is Nabisco's claim that the mean weight is 11.3 grams plausible?
No.
No, it is not. They fall, look at that, look at that. They fall 7 point, whatever, I'm not gonna do this right. They fall 7/100ths of a gram short of what they claim. That's unacceptable.
How dare they?
I know, I can't believe the gall of some of these corporations just treating us the way they do. All right. So now we're going to go through a couple examples. This is the last stuff we're going to do today. All right. We are at an ice cream store now. Would you call it an ice cream store? It's not a restaurant. Parlor?
Yeah, parlor or ice cream shop.
Shop. There we go. I kept writing store yesterday. I was like, that seems wrong. Ice cream shop. I like that. And we'll do it the old fashioned way too. SHOPPE, because this is a pretentious ice cream shop. All right. So ice cream scoops at this ice cream shop are supposed to be 2 inches in diameter, according to the store. You sampled 45 scoops and found a sample mean of 1.95 inches and a sample standard deviation of 0.11 inches. Construct a 90% confidence interval for the true diameter. I'm very serious about my ice cream as well. And this wasn't just an excuse to get 45 scoops of ice cream. This was for science. All right. So we need to state the parameter we want to estimate and the confidence level. The parameter we are estimating is mu, which, before I go too far, I don't expect you guys to copy this down. But what I encourage you to do is, as I'm going through the 4 steps of this: state, plan, do, and conclude, I highly encourage you to have your own piece of paper and just kind of write down the parameter, confidence level, all this other stuff. That should be easy enough to follow along with. And then you can kind of compare it to the prompt later when you look at the presentation. So mu is going to represent the true mean diameter of ice cream, of scoops at this ice cream shop. Oops, no, that's okay. We can show that. The confidence level, 90%. Which means I want to go ahead right now and figure out my critical value, T star. But this is where it gets a little bit weird, because I'm going to go back a few slides. So it's a 90% confidence interval. So I've got this column I'm looking at. It was 45 in the sample. But notice 45 is not on this. It goes from 40 to 50. Again, I know it's a little bit hard to read, but this goes between, so at 40, at n equals 40, my critical value is 1.684. And at n equals 50, my critical value is 76. All right, so which one of those do we use? The general rule here is that we always round down. So if we're between 40 and 50, just go down to 40 and use this value. But we have another method to get the exact critical value. So this is maybe a bit of overkill to what we're about to do, because notice there's only 0.008 of a difference between those two. So it's not the end of the world, either one. But if you want to get the exact value, we can do that. And remember, your critical value is determined by an inverse calculation. We did inverse norm to figure out some critical values yesterday. There's a special one for t distributions. If you go into your distributions on your calculator, you can go down to number 4 and it says inverse t. Okay. Hopefully you guys are following along with that. Inverse t gives you 2 inputs. One of them is area, one of them is degrees of freedom. Your degrees of freedom is going to be 44. That's the 45 minus 1. So your area, it's easy enough to do this. You don't even have to think hard. If you look up at the very top of this column, every one of them has a tail probability. So this 0.05 will be my area. So if it was a 99% one, I'd come over here and use the 0.005 for my area. So 0.05, 44 degrees of freedom. We're going to see a negative number, but that doesn't matter much. So if I wanted the exact critical value, it's either going to be, or I'm sorry, the exact critical value is going to be 1.680. Now, AP test takers and people, well, every one of you, because this will be on your test as well, it does not matter to me which of these two you use, but you shouldn't use this one. You want to round down. The reason for it, round down in your sample size, this gives us a more conservative, wider confidence interval. If we can't get the exact value, go a little more conservative, go slightly wider. Notice 1.676 will make our number of standard errors just a little bit narrower. And we want to widen it out to make sure that it's capturing as much as possible, going a little bit overboard. Okay, so barely makes a difference, but we'll use one of these two values here in a minute. All right, and I'll get back over to that. Okay, so let me erase all this. And the whole point of that little field trip we just did was to figure out our critical value. 1.680 is exact, 1.684 is acceptable. I'll use one of those two in a minute. Now we can move forward. Name of the procedure. And we didn't talk about it too much, but this was a one sample T interval for mu. So now we have two inference methods. Remember, inference, we're making claims about the population based on one sample or maybe two samples. Anyways, our inference method, we have two of them to pick from. We could do a one sample Z interval for proportions or one sample T interval for mu, for means. All right, our conditions. Is it random? I'm going to be a little bit lazy on this part. Is it random? Let's see. It never says that it's random, but if I'm getting 45 scoops, and I'm going to assume that I don't do this all in one day, though maybe some people would. I'm going to assume I want like 45 different days. It's fair to say it's going to be a random selection. People aren't sitting there with their calipers measuring their 2 inches scoop. All right, so yes, it is random. We'll say that. Is it 10%? It's fair to say that 45 scoops is less than 10% of all the ice cream scoops that this ice cream shop could sell. So I think we meet that. And is it normal? Well, our sample size is greater than or equal to 30. So in this case, yeah, we're good. It's normal. Okay, so now we're going to do the calculations. We're good on everything so far. The general formula. And remember, it's always a good idea to start at general and work our way toward more and more specific, plugging in the numbers only at the very end. So it's stat plus or minus critical value times standard error. We can get more specific because we're dealing with means. And this is the same for proportions or means, which is why we write down the generic one. But now we're going to get specific to means, and it's going to be X bar plus or minus our T star is a critical value times our standard error is going to be sample standard deviation divided by the square root of n. And just to repeat myself on one other thing, this right here is in the formula sheet. You don't have to have that memorized. All right, and now I'm going to start plugging my numbers in. At this point, you guys can do the rest of the calculation. So maybe I'll just leave this to you guys, and you can calculate that confidence interval, and I'll just put right here for someone to fill in. Okay, so we do have the answers showing up now. And if you're not done yet, you can continue working on it. All I'm going to do for a minute is write in the calculation with the numbers plugged in, just in case someone got messed up along the way and didn't come up with that. Okay. So if you completed your calculations, make sure that at your starting point, you had those numbers plugged in. And I'm hopefully not rushing anybody. So we can come back to this if there are any questions, something that you didn't have enough time to fully absorb. Okay, now we're going to interpret our interval in the context of the problem. We have a template for this. It doesn't change for this, the fact that it's means. My template is still the same. And actually, before I write it down, what I want you guys to try, I'm not going to read this out loud as I write it. I'm just going to write it on the screen. I want you guys to try and write your own summary sentence of this confidence interval and then compare what you wrote down on your paper to what I am writing on the screen. Okay, so I wrote my interpretation there. Hopefully you guys were trying this on your own. But this just follows the same template that we've been using. We are 90% confident that the interval from 1.9224 inches to 1.9776 inches captures the true mean diameter of scoops at this particular ice cream shop. So the most important question of all, is the ice cream store claim of a 2-inch scoop diameter plausible?
No.
No. Just like Nabisco, this place is cheating its customers. I think a class action lawsuit is required. So that is outside of the confidence interval. So we're going to go ahead and say no to that. So that is all we've got as far as what I'm going to run through today. There is another example. I'll just bring it up real quick. So you can, I'm not going to go through this example. You guys can try using what we just did before. And anyways, give that one a go. And you can answer that question. And here's your homework for tonight. I wanted to point out with these that 1 through 17 really go through a lot of different concepts related to confidence intervals. So I highly encourage you to look at all of them. And of course, answer the ones that you really are struggling with so that you can focus on those questions. The progress checks, I added 2. It's one assignment. It was technically 2 progress checks. It's AP Unit 6, Part A, and AP Unit 7, Part A. Those 2 are available. They're both dealing with progress checks. Remember that your multiple choice questions are going to be based on these types of multiple choice questions. So I highly encourage you to go through this over the weekend and on Monday. We're going to review on Monday, and Tuesday is the test. If you are satisfied with your care, you can log off and enjoy your weekend. I'll see you on Monday. But if you have any questions, feel free to stick around.